today we are going to read our next unit, Uncertainties and Errors, which is 1.2. This section introduces the basic methods of dealing with the experimental errors and the uncertainty in measured physical quantities. Physics is an experimental science, and often experimenter will perform an experiment to test the prediction of a given theory. Of course, like many physicians and many people, they do it practically and by doing experiments to prove a theory. So no measurement will be ever completely accurate. However, so the result of the experiment will be presented with an experimental error. So there can be many answers, and we are not sure that all of them are accurate or not. So there are some uncertainties or errors in them. So okay, and the learning objectives today is like we will learn the distinguish between the random and the systematic uncertainties, and work with absolute, fractional, and percentage uncertainties, and use error bars in graphs, calculate the uncertainty in a gradient or an intercept. So, type of uncertainty. There are two main types of uncertainty or error in a measurement. They can be grouped into systematic and random. Although in many cases it's not possible to distinguish clearly between the two. We cannot distinguish between these two are systematic and random. We may say that random uncertainties are almost always the fault of the observer, whereas systematic errors are due to both the observer and the instrument being used. So the random uncertainties are almost always the fault of these random uncertainties are always due to the fault of the observer, but the systematic errors are due to both the observer and the instrument being used. Maybe if we take an example like instrument like the scale, like old wooden scale, or maybe we can take the metal scale, like the readings that are marked on the scale are, they are like after a certain period of time everything gets old, and after many wear and tears. Okay, so in practice all uncertainties are a combination of the two. Systematic errors. A systematic error biases measurements in the same direction. The measurements are always too large or too small. Measurements are always too large or too small. If you use a metal ruler to measure length on a very hot day, all your length measurements will be too small because the meter ruler expanded in the hot weather, because metals expand in the hot weather. Like in just an example, just like in 40 to 50 degrees, if you use an ammeter is to measure the current, so that shows a current of 0.1 ampere even before it is connected to a circuit. Every measurement of a current made with this ammeter will be larger than the true value of the current by 0.1 ampere. Suppose you are investigating Newton's second law by measuring the acceleration of a card. Like here we have the card. So by measuring the acceleration of the cart as it is being pulled by a falling weight of the mass m, okay, in figure 1.1. So here we have a block of mass m. M is usually not the mass, and this is the cart with the two wheels, and if we drop this box, then the weight of due to the weight of this box, this will move down due to this a downward arrow showing the movement of the mass m. So and then the cart will move in this direction like the arrow here pointing. So and then almost certainly there is a friction force F between the cart and the table surface. There is some kind of friction force between the cart and this wooden surface. Okay, so if you forget to take the force into account, you would expect the cart's acceleration A to be acceleration equal to mg upon m. Mg is like the weight, mg like mass, and the gravity, they both will tend to move in the same direction, their force will be in the same direction, like the mass and the gravity is in the same direction. So, and the capital M, we take it's like a constant mass, like let's see, when M is a constant combined mass, yeah, it's the combined mass of the card and the falling block. So the graph of the acceleration versus M would be a straight line through the origin as shown by the red line in figure 1.2. If you actually do not experiment, you will find that you do not get a straight line, but not through the origin blue line in figure 1.2. Okay, there is negative intercept on the vertical axis. Okay, so here we have the red line and here is our blue line. Okay, so here we have the acceleration, which has unit of meter per second square, and here we have the, like, this x-axis is for mass and we'll measure in kilograms. So now it's like showing the variation of acceleration with the falling mass, like with the blue, and the red one is like without the friction force. Oh yeah, it's written here, this thing. So we can actually see the intercept, negative intercept is like here, like the falling mass, and yeah, through the vertical axis. So this is because with the frictional force present, Newton's second law predicts that A equal to acceleration equals to mg upon m, with the difference of like the minus f over capital M. Capital M, remember, capital M is the combined mass of the block and the mass of the block. Sorry, the card and the mass of the block. Yeah, this thing and mass of this card. So, and this F is the symbol for frictional force. I think everyone is familiar with the frictional force. Frictional force is the opposing force uh, to the movement of the object. Like if the object is moving towards the right, like we can take this an example. The cart is moving like the in the direction of the red arrow, like to the right. Then friction would be in the opposite direction. It would oppose its movement. Friction would be like in this direction, opposite direction, like in the left direction. Okay, so a graph of acceleration a versus mass m would give a straight line with a negative intercept on the vertical axis. Systematic errors can result from a technique used to make a measurement. Okay, there will be a systematic error in measuring the volume of the liquid inside a graduated cylinder of the if the tube is not exactly vertical. So if we have a cylinder, like cylinder is like what we say, if we take a beaker, like a beaker, so and we fill it with some liquid like the water and put a stick, like the glass stick, in it, then we can see, if and we look at the readings, then there are some errors, and let's read about that. The measured values will always be larger or the smaller than the true value. See the true value, like there, this is exactly what I am talking about, the errors. Depending on which side of the cylinder you look, there will also be systematic errors if your eyes are not aligned with the liquid, if you like, if you are not looking straight to the level of the liquid. And similarly, systematic error will arise if you don't look at an analog meter directly from above. Systematic errors are hard to detect and take into account. Yeah. So yeah, like we were talking about this error. This is known as the parallax error. Oh yes, this is written here. This is the parallax error. Like if we, this is due to the error because the person has not kept this cylindrical beaker properly, and so the liquid will be like this. And if the person is observing like straight, is standing from here, he will observe like the level is this, but if he is observing from here, then he might see the level like this. So this is what we say parallax. And if we have straight line, if the person is uh, watching from the top like the above, he will like see the label like this. If the another person is watching like below, and he will see different readings. So this h- the smallest change can bring a huge difference in the reading. So be careful. So random uncertainties, the presence of random uncertainty is revealed when the we are talking about random uncertainties. Right, so the presence of random uncertainties is revealed when the repeated measurements of the same quantity show a spread of values, some too large, some too small. So it is only revealed when repeated measurements of the same quantity show a spread of values, like they have many such values. So some too large, some too small. So there are many uncertainties and errors. Unlike the systematic errors, which are always biased to be in the same direction, random uncertainties are biased. Suppose you ask 10 people to use stopwatches to measure the time it takes an athlete to run a distance of 100 meters. Like you take 10 people to use stopwatches. Like if you use 10 people and ask them to start their stopwatch and measure time taken, and put one of your friends tell one of your friends to run, and at different when he comes across that each when he comes across each student or your friend, then tell them to start the stopwatch and like take their readings. So if we have that, then we have many different readings. So they stand by the finish line and start their stopwatches when the starting pistol fires. Yeah, is that what I was explaining? You will most likely get 10 different values for the time. This is because some people will start or stop the stopwatch too early or some too late. Yes. You would expect that if you took an average of 10 times, you would get a better estimate for the time than any of the individual measurements. The measurement fluctuates about some value. Yeah, it does. Averaging a large number of measurements give a more accurate estimate of the result. Like, see the section on the accuracy and precision overleaf. Like if we include with random uncertainties, reading uncertainties, which really is a different type of error altogether. These have to do with the precision with which we can read an instrument. Suppose we use a ruler to record the position of the right end of the object, like here. If we use to measure the object, so yeah, we can see the difference, like the two rulers with the different graduation. Top has a weight between an graduation of 0.2 centimeters here, and the other is 0.1. We can see the difference, like the divisions. So the first ruler has graduation separated by 0.2 centimeter. We are confident that the position of the right end is greater than the 23.2 centimeter and smaller than 23.4 centimeter. The true value is somewhere between these bounds. Yes. The average of the lower and the upper bound is 23.3 centimeter, and so we quote the measurement as 23.3 plus minus 0.1 centimeter. Notice that the uncertainty of 0.1 plus minus 0.1 centimeter is half the smallest bit. Yes, on the ruler. This is the conservative way of doing things, and not everyone agrees with this. What if you scan the diagram in figure 1.4 on your computer? If we scan this diagram, enlarged it and used it in your computer to draw further lines in between the graduation, if we enlarge this, then there would be so much, it's infinite distance between them. Then you could certainly read position to better position than the plus minus 0.1 centimeter. Others might claim that they can do this even without a computer or a scanner. They might say that the right hand is definitely short of 23.3 centimeter point. We will not discuss this any further. It is an end as a discussion and at this level pointless. Really pointless. Okay, let's move on further. Oh, now let us use a ruler with a finer scale. We are again confident that the position of the right hand is the greater than 32.3 centimeter and smaller than 32.4 centimeter. Okay. Hmm. So the true value is somewhere between these bounds. The average of the bound is 32.3 centimeters. So we got a measurement of 32.35 plus minus 0.05 centimeter. And now notice again that the uncertainty is plus minus 0.5 centimeter is half the smallest width on the ruler. This gives the general rule for the analog instruments. So this is like a definition highlighted here. The uncertainty in reading an instrument is plus minus half of the smallest width of the graduation on instrument. Yes, plus minus half of the smallest width of the. We have to remember this. So for digital instruments, we may take the reading errors to be the smallest division that the instrument can read. So a stopwatch that reads time to a decimal place, example 25.138 seconds, we will have a reading error of plus minus 0.01 seconds. Yes, because there are two decimal places, and a weighing scale that records a mass of 194.5 gram will have a reading error of plus minus 0.1 gram. Typical reading errors for some common instruments are listed in the table right here. So let's see. Instrument is ruler. Reading error is plus minus 0.5 mm. I think we don't need to remember this. If you want, you can learn, but I will surely learn this. Plus minus 0.05 mm. Micrometer is plus minus 0.005 millimeters. Electronic weighing scale is 0.1 gram. And stopwatch is plus minus 0.01 seconds. So these were the reading errors for the common instruments. So accuracy and precision. In physics, a measurement is said to be accurate if the systematic error in the measurement is small. This means in practice that the measured value is very close to the accepted value for the quantity. Assuming that this is known, it is not always so. Like measurement, when is it said to be accurate? If the systematic error in the measurement is small. We can only say that a reading or measurement is accurate when the systematic error is very much less or small. So this means in practice that the measured value is very close to the accepted value. Like the accepted value is like 100.2, and if you get 100 and point 1, so I think it's accurate. So a measurement is said to now a measurement is said to be precise if the random uncertainty is small. Then this means in practice this that when the measurement was repeated many times, the individual values were close to each other. We normally illustrate the concepts of accuracy and precision with diagrams in figure 1.5. The red stars indicate individual measurements. The let's see 1.5. So the meaning of the accurate and precise measurement, four different sets of the four measurements. These are the like the measurements taken. So like the stars, the red star indicate individual measurements, like the measurements. So the true value is represented by the common center of the three circles. Like this is the common center of the three circles. The bullseye. Okay. So the measurements are precise if they are clustered together. Okay. Like this is clustered together. This is clustered together. Yeah. This is clustered together and this is, and we will see the difference now. So The description of the three of the diagrams are obvious. The bottom right clearly shows results that are not precise because they are not clustered together, but they are accurate because their average value is roughly in the center. Because if they are in center, then only they are accurate and precise. So they are like separate. They are separated here. So they are not accurate and not precise, and here they are like combined together. They are close to each other, but they are not in the center, so they are not accurate, but they are precise because they are close to each other. So here these are like in the same ring, but they are not close to each other that much, like this one or this. So this is not precise, but as they are included in one like this area, so they are accurate. So yeah. So now averages. Let's see. In an experiment, a measurement must be repeated many times, if at all possible. If it is repeated n times and the result of the measurement are x1, x2, and dot 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 xn, we calculate the mean or the average of these values. The x bar is usually not the mean. X bar equals x1, we add up x2 and add up plus xn over capital N. So capital N is like the whole number of things we have. So this average is the best estimate. This like we are finding the mean or the average. Yeah, quantity x based on the n measurements. What about the uncertainty? The best way is to get the standard deviation. Let's see of the number standard deviation of the n numbers using the calculator. Standard deviation will not be examined, but you may need to use it for your internal assessment. So it's good idea to learn it. You will learn it in your mathematics classes anyway. The standard deviation, this is like the sigma, sine of a sigma of the n. Standard deviation, remember the symbol, by given by the formula, and the calculator finds this very easily. So sigma is root over x1 minus the mean value whole square plus x2 the second value minus the mean value, and we add up like this and the final value and taking out the difference and squaring that, and over capital N minus 1. So like this is a very simple rule. So delta x, like we have to find a larger difference, like x maximum like the from the maximum point, and the x minimum like from the minimum, and O over 2. So the half of the difference between the largest and the smallest value. For example, suppose we measure the period of pendulum in seconds, like the 10 times, 1.20, 1.25, 1.30, 1.13, 1.25, 1.17, 1.14, 1.32, 1.29, 1.30. We calculate the mean. We calculate the mean by this method. Okay, t bar is equals t1 plus t2 plus dot dot plus t10 over 10, like they have the total number is 10, so and they get this value if we calculate. And the uncertainty, we can calculate uncertainty by doing this, like the t maximum value is here. What is the maximum value? 1.41 is the maximum value. And what is the minimum value? Minimum value is 1.13, so and over 2, if we divide it, so 0.140 seconds. Yes. Okay, how many significant figures do we use for uncertainties? The general rule is just one figure. We just have to use one figure. So here we have delta t equals 0.1 seconds. The uncertainty is in the first decimal place, and the value of the average period must be expressed in the same precision as the uncertainty. That is here to one decimal place. T bar is equals 1.3 seconds. We then state that period equals 1.3 plus minus 0.1 seconds. So notice that the each of the 10 measurements of the period is subject to the reading error. Since these values were given to the two decimal places, it is implied that the reading error is in the second decimal place, say, let's say 0 plus 1 is 0.01 seconds. Like, see this highlighted thing. The value of the average period must also be expressed to the same precision as uncertainty. Okay, so here is a little exam tip here for everyone. There is some case to be made for using two significant figures in the uncertainty when the first digit is in the uncertainty, like when the first digit is in uncertainty is 1. So like this example, since delta t equals 0.140 seconds does begin with digit 1, we should state delta t equals 0.14 seconds and code the result for the period as period equals 1.26 plus minus 0.14 seconds. Yes. So this is much smaller than the uncertainty found above, so we ignore the reading error here. If instead the reading error were greater than the error due to spread of the values, we would have to include it. Instead, we will not deal with cases when the two errors are comparable. So like here, here like it says that instead of like the reading error, we have like the error were greater than the error due to spread of values. If we have like a huge amount of values, like we have taken different values and they are like different, so the chance of error is high, so just we would have to include it instead. So we will not deal with the cases when the two errors are comparable. Okay, so you will often see uncertainties with two significant figures in the scientific literature. For example, the charge of the electron is quoted as E electron equals 1.6421766565 plus minus 0.000, so on 35 into 10 raised to power minus 19. C is, everyone please guess what is this C? This is Coulomb, Coulomb, the unit of charge. So the mass of electron as Me is mass of electron is 9.10938291 plus minus 0.00 so on 40 into 10 raised to power minus 31 kg. This is the mass of electron. So this is perfectly all right and reflects the experimenter's level of confidence in his or her results. Expressing the uncertainty to two significant figures implies a more sophisticated statistical analysis of the data than is normally done in a high school physics course. With a lot of data, the measured values of electron E form a normal distribution with a given mean 1.6021766565 into 10 raised to the power 19 C, and standard deviation is 0.00 and so on 35 into 10 raised to the power minus 19 C. The experimenter is then 68% confident that the measured value of E lies within the interval this or this. So he's pretty much sure. Now we have a worked example here. Okay. So the diameter of a steel ball is to be measured using a micrometer. Okay, micrometer is so small. Caliper, like the vernier calipers, I think. The following are sources of error. The ball is not centered between the jaws of the caliper. Oh, it's the question is talking about vernier calipers. Like, okay, the jaws of the caliper are tightened too much. Okay, third one, the temperature of the ball may change during the measurement. Okay, okay. The ball may not be perfectly round. It can be. And determine which of these are random and which are systematic sources of error. Source is 3 and 4 lead to the solution it gives here is sources 3 and 4 lead to unpredictable results. So They are random errors. Yeah, third one, like the temperature of the ball. They were unpredictable. How can they predict like the temperature? So the source 2 means that the measurement of the diameter is always smaller since the calipers are tightened too much. Yeah. So this is the systematic source of error. Source 1 certainty leads to the unpredictable. They cannot, unpredictable is like they cannot predict the results depending on how the ball is centered. So it is a random source of error, but since the ball is not centered, the diameter measured is always smaller than the true diameter. So this is also a source of systematic errors. Now let's move on. So the propagation of errors. Propagation of uncertainties, not the errors. A measurement of the length may be quoted as capital L equals to it just an estimate. 28.3 plus minus 0.4 centimeter. The value 2.28.3 is called the best estimate or the mean value of the measurement, and the 0.4 centimeter is called the absolute uncertainty in the measurement. Hmm. So 20 points is the best estimate or the mean value of the measurement, and 0.4 centimeter is the absolute uncertainty. So now the ratio of the absolute uncertainty to the mean value is called fractional uncertainty. Like here, if you all want to learn this fast, then just see that we say this the first value 28.3 as the best estimate value or like the mean value of the measurement, okay, and the second one is like the absolute uncertainty 0.4, okay, in the measurement. Just learn the simple concept. And now the ratio of the absolute uncertainty, which is like this, to the mean value is the fraction. If we do it like, if we do it like the like this 0.4 over 28.3, like this is the fractional uncertainty. Let's see, multiplying the fractional uncertainty by 100 gives the percentage uncertainty. Yeah. So let's see here, absolute uncertainty is 0.4 centimeter as we have here, and fractional uncertainty is 0.4 over 28.3 equals 0.0141. So this, if we divide them, then this is what the we get the fractional uncertainty, and the percentage uncertainty is if we multiply the fractional uncertainty with 100 percentage, which gives 1.41%. So this is this was all about absolute uncertainty, fractional uncertainty, and percentage uncertainty. I hope you guys remember it. Okay, so let's move on. Now, in general, if A equals a 0, or some people say it a naught plus minus delta A, we have absolute uncertainty equals delta A, fractional uncertainty delta A upon over A naught, percentage uncertainty delta A over A naught equals 100. This is like just to give a formula, like A naught here represents the mean value or the estimated value. Yeah. So the subscript 0 indicates the mean value. Oh yes, this subscript in written in the subscript 0 is like to indicates the mean value. That's what I was saying. And the A naught is the mean value of A. Okay. So suppose that three quantities are measured in an experiment, like A equals A0 plus minus delta A, and B delta A is, you know, absolute uncertainty. Okay. So b equals b naught plus minus delta b, c equals c0 plus minus delta c. We now wish to calculate quantity q in terms of abc. Okay, if we wish to calculate quantity q, okay, for example, if abc are the sides of the rectangular block, we may want to find q equals ab, which is the area of the base, or q capital Q equals 2a plus 2b. Okay, which is the perimeter of the base, or the Q equals ABC, which is the volume of the block. Okay, yeah, volume. You all know the volume. The formula of volume of the like the rectangular block is like LBH, like the length, B is like the width or the breadth we say, and H is the height. So LBH, like here ABC is like the length, width and height. So yeah, and because uncertainties ABC, there will be an uncertainty in the calculated quantities as well. How do we calculate the uncertainty? That's the question. There are three cases to consider. We will give the result without proof. We will. Okay, so addition and subtraction. The first case involves the operations of addition or subtraction. For example, we might have q equals a plus b, or q equals a minus b, or q equals a plus b minus c. Then in all cases, absolute uncertainty is q. Is the sum of uncertainty in q is the sum of the absolute uncertainties in a, b and c. Like q equals a plus c, we add them, and here we take out the difference, a minus b, and q equals a plus b minus c. So here delta q equals delta a plus b, delta q equals delta a plus b, and here also they would ignore just the negative sign and just put the positive sign. So delta q equals delta a plus delta b plus delta c. So here there is also an example for us. So in addition and subtraction, we always use absolute uncertainty and never subtract. Okay, so we never subtract and just add this. So let's see the worked example. Worked examples are so much important for us to clear our concepts. Okay. The side A of a square is measured to be 12.4 plus minus 0.1 centimeter. Find the perimeter P of the square including the uncertainty. Because if we look at the solution, P equals, do you guys know why it has written 4 is here? 4 is are because they are talking about square. Square has four sides and one side of square is A, so all other three sides, including the fourth side, all the four sides are equal, so all would be a. So a plus a plus a plus a. The perimeter is 49.6 centimeter. Okay, because look at here, and the absolute uncertainty in p is delta p equals delta a delta a delta a delta a, and delta p we can write 4 into delta a. Okay, so delta p equals to 0.4 centimeter, because here absolute uncertainty and delta a is also the absolute uncertainty. So 0.1 into 4, we get 0.4 centimeter, and here we get the final question was like the find the perimeter p of the square including the uncertainty. Okay, so we have got the perimeter as 49.6 centimeter, and with the with the uncertainty also, it would be 49.6 plus minus 0.4 centimeter. Okay, I hope everyone understood this question. So yes, now example 1.8, find the percentage uncertainty in q, which is the quantity a minus b, where a equals 538.7 plus minus 0.3 and b equals 537.3 plus minus 0.5. Okay, and now comment on the answer. Okay, let's comment on the answer. The calculated value is 1.7 and absolute uncertainty is 0.3 plus 0.5, which equals 0.8. So q equals 0. Not 0. Q equals 1.4 plus minus 0.8. The fraction uncertainty would be like the absolute uncertainty over the mean value or the estimated value. Okay, so it would be 0.8 over 1.4 equals 0.57. So the percentage uncertainty is 57%. Okay, percentage uncertainty is like if you multiply 0.57 into 100%, then we will get 57%. Now the fraction uncertainty in the quantities a and b is quite small. Yeah, but the number are close to each other, so their differences is very small. This makes the fractional uncertainty in the difference unacceptably large. Now, here comes multiplication and division. Okay, this second case involves the operation of multiplication and division. Here, the fractional uncertainty of the result is the sum of the fractional uncertainties of the quantities involved. Okay, so like here, fractional uncertainty of the result is the sum of the fractional uncertainties of the quantities involved. Like, let's see here, if q and a and b like the two digits, we have to multiply them. Ab is like to multiply, and a over b is like to divide them. A into b over c is like to multiply a and b and dividing by c. So let's see, uh, like the uncertainties we get like delta q over q0 equals, we just simply add them, never subtract, just put the addition symbol between them and just add them, like the sum of fractional uncertainty. This is the fractional uncertainty that I had explained you before. Okay, so if there is a over b like the dividing them, then also you have to like add them, and if it is like a into b over c, then also you have to like the three uncertainties, you have to add up the fractional uncertainties. Okay, now the power and roots. The third case involves calculation where the quantities are raised to power or roots. Here, fractional uncertainty of the result is the fractional uncertainty of the quantity multiplied by the absolute value of the power. So q equals a raised to power n. Okay, so now what so we can do like delta q over q not q0 equals like this bar. We say it like more like this is in many students, like I also say it like mod. So n is like a number, like it cannot be, if we have a negative number here, then also it would be positive because it has two bars, which means mod. So delta a over a naught, which is the fractional uncertainty here. Okay, so now q equals to and root over a. Okay, now delta q over q0, it will be 1 over n delta a over a 0. Here we have another example. So the sides of a rectangle are measured to be a equals 0.5 centimeter plus minus 0.1 centimeter and b equals 5.0 centimeter plus minus 0.1 centimeter. Find the area a of the rectangle. We have to find the area. Okay, and we have these values. So the fractional uncertainty in a, first we have to find the uncertainty in a. So delta a over a, delta a is 0.1 and delta b is 2.5. So uh, I would request children to like please don't look at the solution first. I cannot hide it. I can only hide it like this. Okay, so first try it yourself and then look at the solution. If your answer is incorrect, if your answer is correct, then it's very good and give yourself a 5 star. And okay, so we have to find the area a of the, okay, so we have to like first find the fractional uncertainty in a. So it would be 0.1 over 2.5 centimeters, and fractional uncertainty in b would be 0.1 over 5 centimeters. Okay, and then I had the solution like when we get this, so the fraction uncertainty like we got like 0.04, 0.02. So and we get the fraction sorry, the percentage uncertainty like 4% and 2. We add them, we get 0.06 or 6%. Then we have finally we had to find the area. So like this we will find the area. 2.5 into 5.0 equals 12.5 centimeter squares, and delta a over a naught would be 0.06. So delta A equals 0.06 into 12.5 equals 0.75 centimeter square, because its area and unit is so much important in physics. If you don't write the unit, you don't get full mass, and hence A equals 12.5 centimeter square plus minus 0.8 centimeter square. So the final absolute uncertainty is equal to 1 significant figure, because it is the least significant figure here. Now, we have another example. Okay, the a mass is measured to be m equals 4.4 plus minus 0.2 kg, and its speed v is measured to be 18 plus minus 2 meter per second. So find the kinetic energy of the mass. The kinetic energy is capital E equals 1 over 2 mv square. So the mean value of the kinetic energy E0 is E0 equals half into 4.4 into 18 square, which equals 112.8 joule. Using this, delta E over E naught equals delta M over M0 or M naught plus 2 into delta V over V0. Because of the square, we have 2 here. Remember, we had the formula, like we will look at the top here. A raised to power n, and n would come here in the multiplication. Okay, just remember the formula. So delta E over 712.8 equals 0.9. We calculate all this, and finally we get this answer, 190.8 joules. Then converting them to the nearest significant figures, and then we get the uncertainty delta equals to 200, which also equals 2 into 10 raised to power 2 joule. That is this, E equals 7 plus minus 2 into 10 raised to power 2. So we have another example tip here. The final absolute uncertainty must be expressed to one significant figure. This limits the precision of the quoted value for energy. Okay, thank you. So the length of the simple pendulum is increased by 4%. What is the fractional increase in the pendulum's period? The period t is related to the length L through t equals 2 pi root over L over g. This formula is for the time period. Okay, L is the length, g is the gravitational force, 2 pi. So because the relationship has square root, then it will be half. Like in here multiplication, there would be half because of the square root. So delta t over t0 equals half into delta L over L0. We are told that delta L over L0 equals 4%. This means hmm, we are told that delta L over L0 equals 4%, and we have, after that we have this, delta t over t is 0 equals half into 4%, which equals 2%. Now we have another example here. A quantity q is measured to be q equals 3.4 plus minus 0.5. Calculate the uncertainty in uh, first part is a, which is 1 over q, and the next part b is q square. Okay, then let's solve a part first. 1 over q is 1 over 3.4, which is 0.29, and this much, and we calculate it by like this, and then finally we get the uncertainty like 0.04325, like 1 over q 0.29 plus minus 0.04, and then q square equals 3.4 square, which also equals 11.5600, and delta q square over q square equals 2 into delta q over q, and delta q square equals 2q into delta q, which equals 2 into 3.5, 4 into 0.5, which equals 3.4, and q square equals 12 plus minus 3. So we get the answer. So our next example, the volume of a cylinder of the base radius r and the height h is given by v equal to pi r square h. The volume is measured with an uncertainty 4% and the height with with which an uncertainty of with this is a type error. So determine the uncertainty in the radius. We must first solve the radius to get r equals root over v over pi h. The uncertainty is then mm, delta r over r into 100% equals half into like the 1 by 2 is half into delta v over v plus delta h over h into 100% and which equals 1 by 2 and in the brackets 4 plus 2 into 100% which equals 3%. Okay, hope you guys are enjoying. Hmm. So the best fit lines in mathematics, plotting a point on set of axes is straightforward. Like in physics, it is slightly more involved because points consist of measured or calculated values, and so is subject to uncertainty. So the point x no x0 plus delta x and y0 plus delta y is plotted as shown in figure 1.6. The uncertainty are like represented by error bars. To go through the error bars, a best fit line can go through the area shaded gray. Oh, area shaded gray. Okay, 2 pi x. Okay. In the physics experiment, we usually try to plot the quantities that will give straight line graphs. The graph in the figure 1.7 shows the variation with the extension x of the tension capital T in the string. The point and their error bars are plotted. The blue lines in the best fit line. It is it has been drawn by eye by trying to minimize the just like just mention it I think. So minimize the distance of the point from the line, and this means that some points are above and some are below the best fit line. The gradient slope of the best fit line is found by using 2 points on the best fit line as far as each other as possible. We use 0, 0 and like this is the point and 0.03907.88 and the gradient is then delta f over delta x and the gradient 7.88 minus 0 over 0.0390 minus 0. So it would be 202 Newton per meter, the gradient. The Westwood line has equation f equal to 0.202x. The vertical intercept is essentially 0 in this equation. X is in meters and f is in newtons. Force f is the force in newtons and x is the distance in meters. On the other hand, it is perfectly possible to obtain data that cannot be easily manipulated to give a straight line. In that case, a smooth curve passing through all the error bars is the best fit line. From the graphs, the maximum power is 4.1 watt and it occurs when R is 2.2. This symbol is, anyone knows what this symbol stands for? This is the ohm, okay, like the resistance. So the estimated uncertainties in R is about the length of the square, so 0.1 ohm. Similarly, for the power estimated uncertainty is 0.1 watt. This power is in watt and this is the resistance, okay, the yeah, the resistivity. So this is the like the you can see the curve. This all is the variation like the power and if we increase this quantity resistivity, the resistance also. So uncertainty in the gradient and the intercept. When best fit line is a straight line, we can easily obtain uncertainties in the gradient and vertically intercept, and the idea is to draw lines of the maximum and the minimum gradient in such a way that they go through all the error bars, not just the first and the last points, like in 1.9. Okay. Mm. So, the best fit line, and the green line is the line through all error bars of the greatest gradient, and the red line is the line through all the bars with the smallest gradient. All lines are drawn by I. The blue line has gradient K max equals 210 Newton per meter, and intercept is negative of 0.18 Newton. The red line has gradient small k minimum is like some minimum value 193 newtons, and the intercept is 0 plus 0.13 newton. So we can find uncertainty in the gradient as delta k equal to k max minus k minimum over 2, and which is 210 minus 193 over 2 and equals 8.5, which is approximately 8 newton meter minus 1. You can have a look at the graph. So now, uncertainty in the vertical intercept is similarly delta intercept is 0.13 minus of and bracket negative 0.18. So minus and minus, like the negative and negative sign is always positive over 2. So it will be 0.155, which is approximately 0.2, like just take the estimate approximate. We saw earlier that the line of the best fit has a gradient 202 Newton per meter and zero intercept. So we quote the result as k equals 0.02 plus minus 0.08 into 10 raised to power 2 and intercept 0.0 plus minus 0.2 Newton. Now let's see the nature of science here. A key part of the scientific method is recognizing the errors. Yes, we need to recognize the errors and notice them that are present in the experimental technique being used, like the technique that the person is using or the child is using, and working to reduce these as much as possible. We just have to reduce the errors as much as possible. And in this section you have learned how to calculate errors in quantities that are combined in different ways, like we've learned now, and how to estimate errors from the graphs. To have also learned how to recognize systematic and random errors. No matter how much care is taken, scientists know that their results are uncertain, but they need to distinguish between inaccuracy and uncertainty, and to know how confident they can be about the validity of their results. The search to gain more accurate result pushes scientists to try new ideas and refine their technique. There is always the possibility that a new result may confirm the hypothesis for the present, or it may overturn current theory and open up a new area of research. Being aware of the doubt and uncertainty are keys to driving science forward. Okay, I hope everyone you remember everything, and just if you didn't get anything, just watch the video again, and if you like the video, then please hit the like button and subscribe the video, and bye bye and have a nice day.